Okay, so I'm assuming you already watched the first long video that I gave you. Obviously, that was going to be that long because it's covering the whole content of the presentation. That was planned for a 1 hour class with your questions and my explanations. That's probably the time that it would have taken us. So let's move to the last slide of that presentation, or at least of that section about stellar processes, and it's slide number 9. The title of that slide is From Luminosity Mass to Age Mass in Main Sequence Stars. So obviously the first thing to remember is that everything we say here is going to be valid only for main sequence stars. The main reason being that everything that we're going to say comes from the mass luminosity relation, and we know that that's only valid for main sequence stars. So the mass luminosity relation, we know it is states that luminosity is proportional to mass to the power 3.5. That 3.5 is the agreement that we have for IB purposes for the value of that exponent, because we know that it's not like an agreed and unique value, but it might change depending on the references that you check, but we're going to work with that one. So we're talking about main sequence stars. We know that the luminosity is proportional to the mass of the star, and we use this relation to estimate the mass of some stars, main sequence stars, depending on how their luminosity related to the luminosity of the sun. So we got an idea of how much heavier than the sun they are by looking at their luminosities. What we're trying to do here, as with the rest of the topics that we've covered, is we're trying to extend a little bit what we knew. So we're going to take this relationship of luminosity and mass, and we're going to try and link it not only to the mass, not only mass to the luminosity, but mass and age of the star. So the first thing that we're going to say is that, well, this luminosity, being power, because luminosity is power radiated by a star, is energy over time. So that luminosity will be energy over time, and it will be proportional to the mass times to the power of 3.5. Now, the important thing to observe here is that this E, this energy that we're writing here, will be understood as the energy radiated by the star during its whole life. And that's a very interesting thing, because we're taking things larger scale, if you want. We're looking at things not in the scale of how much energy it produces in a certain amount of time, but we're looking at the amount of energy that it produces during its whole lifetime, and consequently the time will be obviously the lifetime of the star. Oh, damn it. Of the star. So that being said, this T will give us the ability, this T here will give us the ability to connect to the mass if we can somehow link the energy to any of the other variables for the stars. So let's do that. Connected to this idea that we're looking at the whole lifetime of the star is the assumption that we're going to make for the next step. So that assumption will be that the energy that the star radiates during its whole life comes from converting all that mass that it has into pure energy. Now, we know that mass can be converted into energy because we've studied nuclear reactions where that happens. So NE, that energy is comes better from the whole, I need to deactivate this, comes from the whole mass of the star being converted into energy. Star being converted into energy. And we know, thanks to Mr. Albert Einstein, whose birthday was a couple of days ago, on Pi Day, if you didn't know, that energy will be equal to mc squared, right? So if we assume that all the mass of the star is being converted into energy, then the amount of energy that the star will radiate during its lifetime will be equal to mc squared. Now, if that's the case, then we can rewrite that equation above and say that mc squared over t is proportional to m to the power 3.5. Now, we need to do a little bit of manipulation, but we can see now how things are actually looking good, because we have mass and time, which are the two variables that we need to relate. So let me just rearrange this and say c squared over t then will be proportional to m to the power 2.5. If you saw what happened, I just basically took the m on the left side and divided that, so we can get that 3.5 down to 2.5. And if that's the case, then what we get is something like this. We get m to the 2.5 times t is proportional to c squared. What I did, if you notice, was I flipped around the equation, so the t that it's right here on the left side went up and multiplied the m to the 2.5, and the c squared remains on the other side. And what I get after that, as with any proportion, well, the first thing you need to notice is that this is a constant value. So if this is proportional to c squared, basically what that means is that this whole term, m to the 2.5 times t, is also a constant. So that means I'm going to write it like that: m to the 2.5 times t is a constant, right? A constant that obviously has to do with c squared, but that it's not the main thing. The main thing is that the m to the 2.5 times t is a constant. So you could actually use this to compare masses and ages of stars. You could easily say mass of star 1 to the 2.5 times lifetime of star 1 should be equal to mass of star 2 to the power 2.5 times the lifetime of star 2. So you could end up with something that says T1 over T2 equals M2 over M1 to the power 2.5, which is basically telling you that the ratio of the lifetimes of the stars is actually inverse to the ratio of the masses of stars, because if you see on the left side we have T1 up, but in the right side we have M1 down. That means that if T1 over T2 increases, then M1 over M2 increases too. So long story short, what that is telling you is that a high mass means means a low T. So if you wanted to put it in more dramatic terms, you can say heavy stars die young, which is very sad for them, but it's just what it is. What you need to keep in mind is we start from the luminosity mass relationship. We connect luminosity with energy over time because it's power, and power is energy over time, but that energy and that time is taken as an average over the whole lifetime of the star. So energy becomes the whole energy, time becomes the whole lifetime. That energy is assumed to be the whole mass of the star being converted into energy through Einstein's equation. And then after you do that, you just put that into the equation and you get this one here. mc squared over t is proportional to the mass, and you can rearrange it however you want. That's absolutely up to you. I just find it convenient to do it this way so we can get to this, because this equation down here tells you that the lifetime of stars in the main sequence and their mass behave in an opposite way. So the heavier it is, the shorter its lifetime is going to be. Okay, so that's it, and that was 11 minutes. So yes, it was shorter than the other one. See you around. Bye bye.